In the next, we will verify the property of PCA from another angle. As we discussed, the variance generally corresponding to how a data sample differs from the other one. So let us consider the pairwise distances between the data samples. Of course, we can use for loops and use the equations to calculate Euclidean distances between vectors, which is not very difficult, but scikit-learn provides us convenient functionalities for this purpose. Let's import the module from scikit-learn. The submodule is called matrix, and there is a sub-module called pairwise. Well, this is a module that is dedicated to calculate a given set of samples or two sets of samples. This submodule contains functionalities allows to measure the similarity or dissimilarity between the samples. We use a function called pairwise distances. The function accepts two sets of samples, but if you provide it with only one set and leave the second set blank, it will calculate the pairwise distances between each pair of samples within the provided data set. Just give the data.data, and by default, the metric is Euclidean. So, how's this one? Check. We expect 150 by 150 matrix. The entries in the distance matrix corresponds to the distance, the Euclidean distance between pairs of samples, such as the ith row and the jth column. That entry in the matrix corresponds to the Euclidean distance between the ith and the jth sample in the dataset. Arranged this way, the distance matrix is of course symmetric. Let's have a look at the example. Let's check. The entry of corresponds to the 5th and the 10th sample. We check two elements in the matrix, the 5th row and the entry in the 5th row of the 10th column and that of the 10th row and the 5th column. We expect exactly the same distance between the pair of samples. Exactly as expected, right? Actually, this distance matrix contains duplicated information, but let's for now forget about the duplication in this matrix. And in the next, we will show how PCA returns us a succinct representation of the data that can reflect the variance in the data. We'll calculate a distance metric between the data pairs, the data sample pairs, but instead of using the raw attributes from the observation, we use the features returned by PCA in the transformed data. And instead of using all the features, we use only the first feature to calculate the pairwise distances. Let's call it a matrix, distance matrix D1. Let us compare the element within D0 and D1. The idea is to plot the distances measures within D0 against that of D1. So more specifically, we do a scatter plot, and in each of the points of the plot corresponding to a pair of samples in the dataset, and we will compare how the distance between that pair of samples are measured using the raw observation, the 4 attributes in the dataset, and that distance measured by the first feature returned by PCA. So shortly, we will plot the element values in D0 against those in D1. To extract the values in the matrix, we use a functionality of NumPy called flatten. Flatten takes all the elements in an array and make them a long one-dimensional array. So we do not need the matrix structure here to plot the relationship between two matrices. We only need to compare the corresponding values between these two matrices. So we plot the flattened version of one matrix against the flattened version of another. Here is our plot. In this plot, each point represents two distance measures between the same pair of data samples. The horizontal coordinate of the point represents the distance measured using the original or the raw observations, and the vertical coordinates represent the distance measured between the pair of samples using only one PCA return feature. So the strong correlation between the distance measured by one single PCA feature and the original distance shows that the feature returned by PCA does represent well the variance within the data. Note that all the points in this plot is below the straight line of x equals to y. That is because on the x-axis, that is the original distance contributed by all the raw attributes of the data, but on the vertical direction, the distance is measured by using only one PCA feature. There are other three PCA features which we haven't used in measuring this distance. So the single PCA feature measured distance must be smaller or at most equal to the original distance. We can investigate how well the PCA feature is by comparing it with other features, such as those attributes, the original attributes in the raw observations of data. We can calculate those distances using the same function, pairwise distances, but with the input using only the first, second, third, and fourth raw attribute of the data. We save those let's call it partially computed distance in these four distance matrices, and using the same strategy, we draw the partially measured distances against the original distance. This plot shows the comparison between the original distance against the distance measured with respect to the first raw attribute of the data. It can be seen that the correlation is much weaker than that between the original distance and that one measured by the first feature returned by PCA. Is the second one. It seems that the third raw attribute also gives a good distance measure, but the point is the PCA algorithm automatically returns a single feature that can measure the distance good, and it is guaranteed that the first return feature will measure the distance well, but it cannot be guaranteed. That cannot be said for any individual raw attributes for the data. And even there is such good measures, it is difficult to know beforehand which one is, and it could be expensive to evaluate the the quality of each single raw attribute. And this is the last one. So this example shows us the first few features returned by PCA can well preserve the variance in the data and can reliably reflect the dissimilarity between samples in the data. Thirdly, PCA also have a good attribute of allowing us to reproduce the data from the succinct representation. In this example, let us see how to use only one feature returned by PCA to predict or to guess the original observation of the data. I construct a data representation that has the same form as the original data and fill it with all zeros. Then we put the first feature returned by PCA to the first column of each row. We run this cell and check what we have of the first 10 samples. The last 3 attributes of each sample are all zero and contains no information, and the first feature of each data sample is the first feature returned by PCA in this transformed data. Note that I adopt this form purely for calling the reconstruction functionality provided by the scikit-learn. In practice projects, when we use PCA in this way, we can only keep the information in the first feature and without duplicating so many zeros in the reconstruction procedure. Okay, let's continue, and we will using this function that is called inverse transform. Look, that is not the inverse transform of the transform data. Rather, we use the inverse transform to transform some data that has been some transformed data that we can consider it as transformed data in its compromised format, because we have put all zeros in the last 3, that is 3/4 of the transformed data, and see how this can be used to recover the original data. Let's run this cell, and in this part I just print the original data. What I use to represent this original data using only one single scalar, because I use only the first PCA feature, remember that. And how about the recovery? Let's check the first data. Look, I use this check index in all these 3 parts. So let's go. In the first sample, we get the original measurement as 5.1, 3.5, 1.4, and 0.2. And the PCA feature is just one number of minus 2.68 something. Using only this one number, the PCA model can be used to recover the approximate version of the original data like this. This 5.1 has been recovered as 4.8 with some errors, but understandable. And this one goes to this, and this goes to this, and this feature goes to this. See, it is pretty a good job for using only one real number, a scalar, to recover 4 attributes. More than that, the recovery, the data recovery is applied to the entire set So not only the PCA model recover a single sample using a single scalar, it can recover all the samples using their corresponding scalar representation. Let's check another example, such as this one. Look, with a slightly increased error, but still the recovery is satisfactory, I think. How about this one? So if you consider those numbers varies from one sample to another, we may understand that why we call that the PCA and its newly constructed representation can reflect the trend of variance in the data. The key concept behind constructing a PCA algorithm is called a covariance matrix. A covariance matrix encodes all the linear correlations between the attributes that can be observed from the data set. The matrix has P by P elements, and the matrix is symmetric. So we need only to consider the upper right or the lower left part of a matrix. And the entry of the matrix of the ith row and the jth column represent the correlation between the ith row, the ith and the jth row attributes of the data. Please do not confuse this matrix as the pairwise distance matrix. The covariance matrix has its size corresponding to the number of row attributes of the data, but the pairwise distance matrix has its size corresponding to the number of data samples. For example, in the iris dataset, there are 150 samples, and each sample contains 4 raw measurements of the flowers. So, for the pairwise distance matrix of that dataset, there should be 150 by 150 entries in that distance data matrix to measure the pairwise distances between each pair of individual flower samples. But for the covariance matrix of the dataset, that matrix should only contain 4 by 4, that is 14 elements, and each of the elements correspond to the correlation between a pair of the attributes. Let us consider an example of calculating the covariance matrix in the simplest data configuration, such as a two-dimensional data space. Consider we have n data samples. Call them x1 till we have xn, and we have two attributes in the raw observation of the data. X1, let us note them as x1 1 and x1 2. Say we have x2 1, x2 2, go all the way until we reach xn1 and xn2. So the first subscript represents the index of data sample, and the second subscript represents the attribute. Let's put this data in a data array called netx. The covariance matrix of this data array would be a 2 by 2 matrix. And each of the elements of the matrix, such as this one, represent the covariance of the first attribute among the data samples. Of course, on this diagonal, we have variance instead of covariance because we are calculating the variance of single variables. But on the off-diagonal elements, such as here, that would be the covariance of attribute 1 against that of attribute 2. To calculate it, the first step, we need to shift the data so to make sure the new center of the data is at the origin of the data space. This step is called centering the data. So let's first calculate the original center of the data. The center of the data is calculated with respect to each attribute, such as we take the mean value of all the first attribute among all the data samples. Let's call it x1 bar. So I put this 1 here as the superscript to represent that refers to the first attribute, and the bar shows denote that is the mean value. And for the second attribute, we can calculate another mean value, call it x bar 2. So from each of the data sample, such as the x1, we can transform it into the centered x1, which is just to subtract the mean value of each attribute from the attribute of that particular sample x1. Similarly, we can calculate the centered version of all the data samples. So the centered data samples, because all the sample attributes has subtract the original mean value, we can expect the centered version of the data sample has its new center at exactly 0, 0. That is the origin of the data space. If we draw it graphically, that would be like if this is a data space and the original distribution is at this point. If we calculate the center of the data distribution, for example, this is x1 bar and this part is x2 bar. So the first step is to move the data to this direction, so the entire data distribution is located at the origin. See, in this way. Because the centered version of the data distribution is around the origin of the data space. So to calculate both the variance or the covariance, we are concerned only with how an attribute varies with respect to the origin with itself, or how two attributes varies together around their origin. The variance of a single attribute would be the summation, the accumulated variance of that particular attribute with itself. Particularly in each term in the summation, the centered version of the attribute is multiplied by itself and divided by n-1. Note, this n-1 rather than n is a statistical technical detail, is to ensure unbiased estimation of the variance of the data population. We should not worry too much about that term, just use n-1 instead of n in the calculation. But in practice, even if you use n in the calculation, the result generally won't be too much different from the n-1 version. The real interest part of the covariance matrix occurs at its off-diagonal elements. Those elements measure the covariance between different attributes in the data. That is, how an attribute varies away from its mean, and in the meanwhile, how that correlated to the variation away from the mean value of the other attribute. That is the accumulated variance among all the samples. The centered first attribute multiplies the centered second attribute and divides the overall accumulation by n-1. The entire operation can be denoted in matrix operations. We can call the data matrix as X and the centered data matrix as X bar. Then the computation above would be the covariance matrix equals the transpose of centered data X bar multiplies the centered data X. Note that in literature, sometimes some people would like to write the data in a transposed form, that is, in the data matrix, each column instead of each row represent a single data sample, and each row instead of each column corresponds to an attribute. If the data is represented that way, we need to write the covariance matrix as X bar multiplies X bar's transpose. Note that the functionality calculating the covariance in NAPI takes the second convention. That is, when you give a data matrix to NAPI's covariance function, NAPI will return a covariance matrix that has the size corresponding to the number of the rows of the input data matrix. That is, using the Euro form of the data matrix as we have done so far, we need to transpose our Euro data matrix before we give it to the covariance function. PCA works by finding a decomposition of the data covariance matrix. So let the matrix to be some summation of component matrices. Let the component to be W1, W2, go to Wn, and each of the component has a scalar factor. So the sum of those components makes the data covariance matrix C. Those component matrix has the very important property that those matrices are rank 1 matrices. That is, they are generated by a single vector. See the attribute. It equals a vector, a column vector multiplies by itself. See the element in a W from W11 to WPP. Note that each of the component matrix is the P by P matrix that is the same size as the covariance matrix C corresponding to the P attributes in the data. W can be generated by a single P-dimensional vector V. We let the W to be the outer product of V by its transpose W11 equals V1 times V1. W12 equals V1 times V2. Wi row to the jth column equals I times Vg. The information in the P by PW is completely inferred from the information in the P by 1 vector V. So we call such a W some rank 1 matrix. Note, there is a scaling factor in the original decomposition of covariance C. So there is some uncertainty in the decomposition. For example, you can increase some generating V by a factor of 2 so that the corresponding component matrix W will be of a magnitude that is 4 times as the previous one. And then you can shrink the scaling factor, the corresponding scaling factor K, by a factor of a quarter. This way, we will arrive exactly the same decomposition as the previous one. So we would like to keep the decomposition unique. We'd like to eliminate such uncertainty. V is a unit vector, which means if we get the norm of V, that is 1. And if we write it up, that is Vg squared. The elements of V, we take its square and take the summation, that equals 1. So this way, we decompose the covariance matrix of the data into component matrices, and each component is represented by a component vector. From all the elaborate derivation above, we can see that those component vectors compactly represent all the possible covariances between the raw observed data attributes, and we can use them as the major component representing the covariance in the data. And so this kind of analytics is called principal component analysis. In practice, one can carry on the derivation, and eventually the math will lead us to a point that we do not actually need to explicitly construct the data covariance matrix, nor need to do the decomposition into the rank 1 matrices of the covariance matrix. One can directly operate on the data matrix, that is called using an operation called singular value decomposition, which is also widely provided by a lot of basic linear algebra libraries. For example, if we have some data distribution in this way, and from the distribution, we observe the training data sample in this two-dimensional data space in this way. And look, the original space, in the original data space, the coordinate is given with respect to such a coordinate system. But after PCA, we might find that the covariance of data is mainly occurs along this direction, and that this blue vector becomes the first unit principal component. After removing the covariance in this way, to decompose the residue of the covariance, we may find the second unit principal component vector in this way, and the second vector by construction will be orthogonal, or, well, generally speaking, that is perpendicular to the first vector, and that is orthogonal and unit principal vectors. Using these two pieces, one can represent the data samples, be that the training data samples that has been used to construct the principal component model, or the newly observed, say, new data samples. All those data samples can be projected to the two principal components. Give example. For example, this sample, the original representation of the sample would be in this way, and that will be the x and y coordinate of this data sample. In the new representation, the sample will be projected to the principal component, and with respect to the new data center, as we introduced in the first step of moving the dataset to the origin. So this would be the new first feature of the data sample of the first feature of this sample, and this will be the new second feature of the sample. So by projecting data samples along the direction specified by the principal component vectors, we represent data using PCA. If you are interested in further applications and the theory behind the principal component analysis, you can go into all the technical details and their programming implementation in the tutorial referred in the slide, and there is also a very good book on this topic.